All right, let's jump right into this explainer. Today, we're totally demystifying the periodic table, taking it from that static poster you probably remember from a classroom wall and turning it into a dynamic, living map of highly reactive metals and incredibly bizarre shape-shifting nonmetals.
Here's our itinerary for today's elemental journey. First, we'll cover the periodic map. Second, we'll meet the representative metals. Third, we'll look at isolating metals from nature. Fourth, we dive into the nonmetal realm. And finally, we'll explore allotropes, the shapeshifters. All right, part one, the periodic map, charting the elements.
You know, it's really best to think of the periodic table not as some boring list, but as an actual geographic map of atomic behavior. Where an element lives on this map tells you exactly how it's going to act. If you look at the representative elements, those are the ones where the s and p orbitals are busy filling up with electrons, covering groups 1, 2, 12, 13, 14, and 15, you'll see something pretty cool. Even though group 12 is technically considered transition elements, that last added electron drops right into an s orbital, so they actually act a whole lot more like representative metals. This specific neighborhood on the map means they are highly eager to ditch their outer valence electrons, which is exactly why they are so fantastic at conducting heat and electricity.
Moving on to part two, meet the representative metals, reactivity and shields. So over on the left side of our map, these representative metals are basically desperate to shed electrons and react with whatever is around them. But there is a massive difference in how they survive out in the wild. On the far left edge, groups 1 and 2, they are wildly reactive. I mean, they're so eager to react with water and oxygen that you are literally never going to find them just sitting around uncombined in nature. But shift just a bit to the right to metals like zinc, aluminum, and tin, and we run into this brilliant chemical trick called passivation. Instead of violently reacting, they slowly react with air to form this tough, invisible, non-reactive oxide film. It's basically a self-protecting shield. That's the exact reason we can actually use aluminum for cookware and foil without it just immediately corroding into dust. And as we stroll through groups 12, 13, and 14, things get weird, in a good way. Take zinc. It's the most reactive metal in group 12, but its reactivity actually goes down as you move down the group, which is the exact opposite of the trend in groups 1 and 2. Or how about gallium in group 13? It has a melting point of just 30 degrees Celsius. That means if you held a solid chunk of it, it would literally melt right into a puddle in the palm of your hand. Then we have aluminum, which is amphoteric, meaning its oxides are flexible enough to brilliantly act as either an acid or a base. Finally, the heavyweights down at the bottom, like tin and lead, show off something called the inert pair effect. This lets them form stable cations with oxidation states 2 full steps below their group average. Next up, part 3, isolating metals from nature, brute force chemistry. Now, because these metals are so incredibly reactive, they're not just waiting around in the dirt for us to scoop them up. We actually have to forcefully rip them out of their natural compounds using some serious industrial muscle. For those highly reactive metals like sodium, magnesium, and aluminum, standard chemical isolation just doesn't cut it. Instead, we use electrolysis. We are pumping massive amounts of electrical energy to forcefully drive otherwise unfavorable chemical reactions to finish. Whether it's the down cell churning through molten sodium chloride or the massive Hall-Harris setup for aluminum, we are literally using the brute force of electricity to shatter those chemical bonds and pull out the pure metal. But hey, electricity isn't the only tool we've got. For some elements, we can use clever chemical reduction techniques, which honestly is usually a lot cheaper. Take the Pigeon process for making magnesium. We actually use other elements as reducing agents. And here's the wild part. We can use a metal like sodium to reduce a metal that's actually more reactive than it is. How? By exploiting volatility. The newly formed metal turns into a vapor, and we continuously distill and collect it. By constantly siphoning off that vapor, we're basically hacking chemical equilibrium. Shout out to Le Chatelier's principle, forcing the reaction to just keep producing more and more of the exact metal we want. All right, part 4, the non-metal realm, a new set of rules. So, as we cross over to the upper right corner of the periodic table, the physical rules of the road completely flip. Welcome to the realm of the non-metals. Right off the bat, these elements ditch the giant, tightly packed metallic structures we were just looking at. Because nonmetals have much higher electronegativities, they prefer to share their electrons through covalent bonds. So instead of a massive flowing sea of loose electrons, nonmetals lock their electrons down. They keep them strictly localized between atoms, forming distinct individual molecules. What really makes this corner of the map so fascinating is the sheer extreme diversity. Just under normal room conditions, nonmetals make up more than half of all the elemental gases, like the diatomic nitrogen and oxygen we breathe every day. There is exactly one liquid, bromine, and the rest? They range from some of the softest, squishiest solids to the absolute hardest materials known to humanity. The specific neighborhood gives us the essential building blocks of all biological life, showing off a crazy variety of physical states, all thanks to the unique ways they bond together. And finally, Part 5, Allotropes, the shapeshifters. We have officially reached the climax of our elemental journey, a mind-bending phenomenon called allotropy. Because nonmetals can link up in different covalent bonding structures, one single pure element can take on completely, radically different physical properties. Just look at pure carbon. Depending entirely on how you arrange its atoms, you get entirely different stuff. Build a rigid 3D grid, and you've got a brilliant diamond. Take those exact same carbon atoms, stack them in flat, sliding sheets, and suddenly it's graphite, the stuff inside your pencil. Peel away just one single atomic layer of that graphite. Boom, you've got graphene, an absolute modern structural wonder. Totally different worlds, but literally all just pure carbon. Let's check out how this shape-shifting trick plays out with another element, phosphorus. The visual contrast here is just wild. First, we have white phosphorus, which is made of these distinct little tetrahedron-shaped molecules. It is intensely reactive, like bursts into flames in the air, glows in the dark, highly toxic reactive. But if you heat it up in the absence of air, it shapeshifts into red phosphorus. Those individual tetrahedrons snap together into a massive 3D polymeric network, instantly turning into a dense, super stable, and mostly non-toxic material that is vastly safer to handle. And then there's sulfur, good old ancient brimstone. It might actually be the most complex shapeshifter of them all. At room temperature, it likes to form these puckered 8-membered rings, S8 molecules. If you melt them, they easily slide past each other as a runny, straw-colored liquid. But watch what happens as you crank up the heat. The single bonds break, those rings pop open, and they start physically tangling into each other. They form these incredibly long, sticky chains, transforming that runny liquid into a dark red, viscous mass that eventually gets so insanely thick it won't even pour out of the glass. So from the passivated aluminum in your kitchen foil to the layers of graphite in your pencil, literally everything around you is a product of exactly where it sits on the periodic map. The next time you grab an ordinary, everyday object, I want you to ask yourself, what kind of violent chemistry, brute force industrial electricity, and invisible atomic shapeshifting had to take place just to put that item into your hand?